Hello everyone. So from the last video we have started discussing the 6 different important reactions under electrophilic aromatic substitution. So in the last video we have discussed sulfonation, nitration. Today we will discuss halogenation. So first we have to see the nature of halogens, that is their activating or deactivating nature, and also the orienting effect. So first we will focus on the activating or deactivating effect. We know that halogens, they have inductive effect, negative inductive effect. So they withdraw electrons by their negative inductive effect, and they have another property that they can release electrons by their plus R effect also. Fine. Now as minus I effect, it is winning over plus R effect. So by their net electron withdrawal, what they will do, they will destabilize the sigma complex that will be formed after halogenation. So this is X, that is any of the halogen you can consider, and this is our incoming nucleophile. This is the sigma complex, that is the intermediate aranium complex. So there is a positive charge generation. So if minus I effect, it is more than plus R effect, so obviously it will destabilize, and as a result there will be slower rate of substitution. So basically it is deactivating group, not activating group. Fine. So that is all about the activation. Next we have to see what is the orienting effect of the halogens. Now for orienting effect of the halogens, we have to look at the relative stabilities of the sigma complexes. So this is the sigma complex. Now there are different resonance structures possible. So we will look at the different types of attack, that is ortho attack, para attack and meta attack. So you can see in ortho attack and para attack there are different resonance structures, but the structure A in case of ortho and structure B in case of para, the positive charge is very close to the halogen. Here Y is actually halogen. Fine. So that means if you consider the negative inductive effect, obviously this will destabilize this positive charge, but that is not present in meta attack. In all the resonance structures you will see the positive charge, it is not close to Y. But here another effect we also have to consider, that is when we are talking about orientation, though plus R effect, here we have written that minus I is winning over plus R, that plus R is weaker, but though it is weaker but more selective, it is showing more selective resonance effect. So in this case, now though inductive effect we have considered for in case of activation, that minus I is greater than plus R, but when we are talking about orientation, it is controlled by weaker but it is more selective, it is showing more selective resonance effect. So now plus R effect is winning over minus I effect. So that is why though halogens are ring deactivators, that is when there is a substituent halogen in benzene ring, compared to benzene, now the rate will be slow compared to benzene. That is when there is a halogen, when there is a hydrogen, that is benzene. So compared to benzene, now the rate of the reaction will be slow. But what will be the position of the incoming electrophile? That is completely controlled by weaker but more selective resonance effect, that is plus R effect. So that means we will get ortho attack and para attack product. So basically it is ortho para directors. Okay. Next we will see bromination. So if our halogen is bromine, then what will be the mechanism? Now in bromination, here we have used FeBr3, which is Lewis acid catalyst. You can also use the mixture of bromine and iron, and in the reaction medium FeBr3 will be produced. But sometimes bromine and FeBr3 that can also be used. So what is the role of Lewis acid? Suppose you are not using Lewis acid, you are simply using only bromine. So you can see there will be no polarity developed. But if you are now using Lewis acid, not just FeBr3, that is the most common, that is why it is written here. So it has electron accepting property. So what it will do, you can see there are lone pairs. So there will be some positive charge generation because iron will withdraw electron density because it has some electron deficiency. That is why it is Lewis acid. So now there is some polarity generation. We can see plus and minus. And if you are breaking the bond, now it is free electrophile, that is Br plus. So that is the generation of electrophile. We have also seen in previous videos how we can generate electrophile. Now we are actually seeing it in detail. So the pi electron cloud of benzene ring, it will attack this bromine, or you can also take directly here Br plus. That is also another possibility. That is the pi electron cloud is attacking the Br plus, that is a free Br plus, or you can directly write this one. Okay, so now this Br bond will be broken, and FeBr4, that will be the side product, and these are the different sigma complex resonance structures. Okay, now finally what will happen, this FeBr4 minus, it will capture this hydrogen. So as a result, aromaticity is regenerated, and we are getting our final product, bromobenzene. And what are the side products? HBr and FeBr3. So you can see our catalyst is again regenerated, which can be again used in the next step. Fine. Energy profile diagram. So the first step, that is the loss of aromaticity, as it is energy demanding process. So that is why the first activation energy compared to the initial, that is the starting material, it is high, but the second activation energy it is low. So first step is slow step, and the second step is fast, when aromaticity is regenerated. Fine. Now we will see some specific examples, that is we will not take benzene as starting material, we will take aniline, anisole and phenol. So first aniline, that is NH2 is attached to benzene ring. We are using, see, 3 bromine atoms. Now there are not just mono substitution, there is tri substitution. Now why it is so? Because NH2 is very activating group. So now the ring is highly activated. So 3 electrophiles are basically attached to the aromatic ring. Okay, so 3 bromine, 3 Br2, and we are using it in water medium, and also we have to use NaCO3 because here HBr will be the byproduct. You can see 3 Br2, that is 6 bromine atoms. So all the bromine atoms on the right hand side, it is balanced, and to neutralize this HBr, which is the side product, we have to use sodium bicarbonate. So if HBr is consumed, then only the reaction will be, that is in the forward direction, it can move easily. Okay, so our product is 2,4,6 tribromoaniline. Next is phenol. Now see, in case of phenol, 2 different conditions we can use. The first condition is aqueous medium, and the second condition is we are using some non-polar solvent. CS2 can also be used. Another example, carbon disulfide. Sorry, that can also be used. So this is polar medium, and the second condition is non-polar medium. So when it is in aqueous medium, what happens? Phenoxide ion is generated, because in aqueous medium, as it is polar solvent, OH bond can easily be broken and O minus is generated. Now when O minus is generated, it is very active, it will activate the ring by resonance, by taking part in resonance with the double bonds in a benzene ring. But if it is the non-polar solvent condition, then this type of ionization will not be there. So now it will simply remain as OH. Now if you compare O minus with OH, obviously O minus, the donating effect is more because there is full negative charge. But in case of non-polar solvent, it is simply OH. So that is why in non-polar solvent we are getting mono-substituted product, orthobromophenol and parabromophenol. But in case of aqueous medium, we are getting tri-substituted product. That is the difference. And here para is major because of the steric problem at ortho position. Now next is anisole. Anisole means methoxy group is there in the benzene ring. So it is also same as that of aniline, you can see. And here also we have to use actually some base so that we can neutralize the side product, that is HBr. So that is all about bromination. Chlorination, that is also just like that of bromination, and sometimes AlCl3 is also used as Lewis acid. FeCl3 can also work. So when it is bromine, we are using FeBr3. When it is chlorine, that is chlorination we are doing, then we have to use FeCl3 or AlCl3. That is the chlorine containing salt. What about iodination? Now if you compare all the halogens F, Cl, Bri, as we are moving down the group, iodine is the least reactive among all the halogens. So except for active substrate, suppose your substrate is not active, simple benzene ring or any electron withdrawing group substituted ring, in that case you have to use some oxidizing agent. All these examples are there. You can use HNO3, HiO3, H2O2 as oxidizing agent. So if it is active substance, suppose aniline, anisole, like that, all are that is activating the group, all are activating groups, that is NH2, OMe. But suppose if it is not active substrate, suppose simply benzene ring if you take, then we have to use some oxidizing agent, so that now the oxidizing agent, it will oxidize the iodine to a beta nucleophile. Okay, sorry, it will be electrophile. So oxidize means it will take electron density from iodine. So see, suppose you are using HNO3, so this type of species will be generated. Now protonated HO, that is OH2, that is attached to iodine. That means it will draw electron density from iodine. So now the pi electron cloud in benzene ring, it can attack iodine and this bond will be broken and H2 will be generated. So our product is iodobenzene. Next we have to see fluorination. So fluorine, FCl-Bri, iodine is least reactive, but fluorine, that is the first halogen, that is very reactive. So what will happen if you want to do fluorination using the similar condition that we have used for chlorination or bromination? What will happen? You will get monofluorinated product, but the yield will be very poor. Why? Because the fluorine is so reactive that there will be so many different types of other product formation. That is the unwanted, undesired product. So though we will get our product, but yield will be very low. So it will be of no use. Okay. So we have to find some solution for that. So to generate F+, there are some other sources that you can use. For example, suppose you have taken toluene, and very good example is select fluor. So select fluor is this molecule. So here you can see, actually F is the most electronegative atom in the whole periodic table, right? So obviously F+, positive charge over F, it is so unrealistic, right? So that is why when there is some highly electron withdrawing group like this, it is attached with fluorine, though it is not free fluorine plus, because that is very difficult to generate. Though here we have written it, but actually free F+, that is very unusual. So when some highly electron withdrawing group is attached, then this fluorine, there will be some positive, partial positive charge. So double bond over, that is a pi electron cloud. Now it can attack this fluorine, and as it is methyl group, it will be ortho-para orienting. So we will get orthofluorotoluene or parafluorotoluene, but see, yield is very good. That is compared to, if you use normal condition, compared to that, now the yield is very good. Okay. And there are some other reagents, though select fluor is best. I have mentioned that also, AgF2, cesium fluoroxysulfate, CSSO4F, and acetyl hypofluorite. That can also be used. Okay. So basically, among these four, that is bromination, chlorination, iodination, fluorination, the most common, most of the time that you will see is chlorination and bromination, because these two halogens are in the intermediate position, right? F, Cl, Bri. F and iodine, they are at too extreme. F is too reactive, iodine is too less reactive. So that is the problem. But Cl and Br, they are examples, that is chlorination, bromination examples are very common. So that's all about halogenation. So I hope if you find the video helpful, Please like, share and subscribe. And for all the related videos, the links you will find in the description box. So in the next video, I'll come with another important reaction, which is Friedel alkylation. Until then, goodbye and thank you for your time.